Hello, I'm Dr. Shakti, and let's talk about dead space, ventilation perfusion, and flow limit in today's lecture. So let's look at dead space first. So some questions about physiological dead space, anatomic dead space, and how it's calculated. So basically, this is the gist of whatever has been asked so far about dead space. So one basic thing that you need to know, dead space comes to around 100 to 150 ml. Okay. Um, so for anatomical dead space, it's through Fowler's single breath nitrogen washout method, and your Boas expired CO2 approach is for physiological dead space. Okay, this again I'm not gonna elaborate on it because it's a concept which will take a lot of time for you to even understand. Okay, I studied this when I was a PG, so I don't think it's necessary for you to understand what is happening here because it's not that important at your level to understand this. Okay, it's not going to help you any further in understanding this. So I'm just gonna give just these details. You just have to study it like this. I'm sorry for that. Okay, so anatomical dead space, Fowler single breath nitrogen washout method. Physiological dead space, both expired CO2 approach. Just remember that. Anatomic dead space and physiological dead space, whatever dead space which is there, which is not taking part in the respiration throughout your tracheobronchial tree, that is your anatomical dead space. But physiological dead space, what it means is, even if its ventilation is there, but if not enough perfusion is there in those areas, in those alveoli, then that will be a physiological dead space because ultimately there's no mixing of air into the blood. And also, even if the RBCs over there are fully uh, taken up all the oxygen, and then there's no more perfusion uh, enough to take in the oxygen, that again leads to your physiological dead space. So this is the difference between anatomical dead space and physiological dead space. So this I explained to you because in options sometimes in true or false and all this might come. Okay, so that is it about dead space you need to know about. During standing in apex of lung, blood flow, ventilation, ventilation by perfusion, and what is the value of ventilation perfusion ratio in different parts. Okay, so this is something we need to understand. So first thing you need to understand is as we go from bottom up, okay, ventilation decreases and perfusion also decreases. So perfusion is easy to understand. When you go from down to up because of the effect of gravity, ultimately the perfusion is going to reduce as you go up. Okay. Um, when you talk about ventilation, the difference in the transpulmonary pressure is different here and here. So you see that the interpleural pressure is more negative here. So we had learned about pump handle mechanism, and we had learned about your bucket handle mechanisms and everything else. So this pump handle mechanism that is over here, along with the rib muscles, the intercostal muscles, with the scalenus, trapezius, all these other muscles that are involved here are much more effective. Okay, so because of that, the interpleural pressure is much more negative at this point in the apex. Okay, and the transmural pressure because of that is more, because more negative means in the equation of transmural pressure it becomes positive, so this becomes greater. Okay, so because of that, what is happening, these are alveoli are more inflated normally at rest. So when it's more inflated at rest, the amount to which it can accommodate is lesser. If it already inflated this much, it can only go to a maximum of this. But in the base, if the transmural pressure is not that high and it's initially like this, and it can accommodate till this level. So the ventilation here ultimately is lesser than here. Perfusion is also lesser on top. But if you look at the ventilation perfusion ratio, the fall in perfusion as you go on top is much more than the fall in ventilation. Okay, so ultimately ventilation perfusion ratio is going to be higher on top compared to below. Okay, so this is something you have to understand. So ventilation and perfusion both fall when you go on top, but the ventilation fall that is there is much less than the fall in perfusion as you go on top. So because of that, the ventilation perfusion ratio increases when you go on top. Okay, so you can take an example with normal values, ventilation of this much, perfusion of this much, ventilation by perfusion will come to around 0.8. So this is a normal average value of your ventilation perfusion ratio that is there. Okay, so this value as we go to the apex comes to around 3 to 3.3, this ratio. Okay, when you go down to the base from 0.8 it will go to 0.6. Okay, so below perfusion is better, ventilation is better, perfusion is a little more than ventilation here. Okay, when you go on top, both ventilation and perfusion are poor, but perfusion is much more poorer compared to your ventilation. Okay, so here ventilation perfusion ratio is 3.8 normal value and 0.6 is at the base. Okay, so these are all questions that will come from this. So another concept is flow limitation, something called perfusion limited. What is diffusion limited? Okay, so we'll come to understand that. So we have the alveoli. There's a partial pressure of oxygen there in the alveoli, and there's the blood vessel. So the oxygen has to go into your pulmonary vasculature. Okay, so what is partial pressure? When you say partial pressure, this is a very important concept. When you say partial pressure is that of the dissolved substance, that particular gas, it's of the dissolved one that you're saying. Okay, so in this whole thing, the amount of oxygen that is remaining dissolved in the whole vasculature, that is what is exerting your partial pressure. Okay, so when oxygen goes from here, alveoli to here, what it does is, for transport of oxygen, it majorly goes through your RBC. Okay, so inside the RBC, in the hemoglobin, that is how transport of your oxygen happens. And whatever is remaining, few is going over here. This is ultimately what happens. So this is the normal transit time for blood to go through your pulmonary vasculation. Okay, so you just say a value of 0.75. Okay, 0.75 second is the transit time for it to move through. Okay, but your oxygen, for it to go into the RBC and taken into the hemoglobin, this whole process takes only 0.25 seconds. And this blood over here, from here to here, when it goes, it just takes a 0.75 second. So that means even before that, at some point it gets fully into the RBC and the remaining starts coming out over here. So at some point what happens, because of this, the partial pressure of oxygen here gets equilibrated with this, because there's a lot of time, 0.25 for this process to take place, then this goes over here, and this point more time that is there, and that will increase your PO2, so that finally when there's no diffusion gradient, it stops. Okay, so this is the whole concept. So when there's no diffusion gradient, there's no diffusion anymore. Okay, so in case of oxygen, the problem is, the limiting factor is your perfusion. So how much blood is there, how much it's moving, and when next blood is coming, that is what is limiting it. If the transit time was much lesser, instead if this was 0.25, every 0.25 second new blood comes, then we won't have a problem. But because this is ending much sooner and transit time is the limiting factor, this is a perfusion limited flow. Okay, so this is a concept that you need to understand. But on the other hand, when you take something like carbon monoxide, So this carbon monoxide, when it goes into the RBC, the hemoglobin has 200 times more affinity than your oxygen to carbon monoxide. Okay, so because of that, this takes longer time. It can take in more carbon monoxide and it takes longer time. So even this 0.75 second is not enough. So that means it's not coming to your partial pressure much. So that means there's no equilibration. It can keep on coming. So here the limiting factor is not how much blood is flowing. Here the limiting factor is how much it can move through this tissue, how much it can diffuse through this. So that is why that is diffusion limited. This is the simple concept of what is perfusion limited, what is diffusion limited. So again, let's take a look at the transit time, 0.75 to 1.12 seconds. So in this transit time, if that particular gas takes lesser time than this, then it's going to be your perfusion limited. If it takes, around this time or more than that, then the problem is not with the perfusion, it's in the same rate or more than that. Okay, but the problem will be in the diffusion, so that is diffusion limited. So example for perfusion limited is N2O. Oxygen, carbon dioxide, they're actually between perfusion limited and diffusion limited, somewhere between, but more towards your perfusion limited. Okay, so if you had to choose an option, you can say that these are actually perfusion limited. Ideal example for this would be this. Okay, and as we had mentioned earlier, for diffusion limited, the ideal answer is carbon monoxide. Okay, and the reason for this is because of its affinity to hemoglobin. Physiological dead space is calculated by, so for physiological, it's going to be a Bose equation. Following used to calculate anatomic dead space. So anatomic is your single with nitrogen. During standing in apex of lung. So in the apex, blood flow is not high. Ventilation is also not high. Ventilation by perfusion is high. So that is the answer. Ventilation perfusion ratio at base of lung. So base of lung is 0.6. Apex is 3 to 3.3. Average is 0.8. Transport of carbon monoxide is diffusion limited because of. So there are various options here. We already know it because of its affinity. So high affinity of carbon monoxide for hemoglobin is the answer. Now another small concept. Partial pressure of oxygen is maximum in. So we already talked about the ventilation perfusion ratio. At the apex, ventilation is better, perfusion is less. At the base, perfusion is good, ventilation is good, but ventilation perfusion ratio, if you look, it's kind of more towards your perfusion. Okay, so in a context of oxygen, which is perfusion limited, if you go to the top apex and there is some sort of perfusion limitation, then the transport of oxygen will be lesser. So more will be inclined to go through your dissolved state. So ultimately, because of that, the PO2 is going to be a little higher in the apex compared to your base. So this is basically what they're asking. So if you understood that whole thing where I explained earlier, you might understand what I'm talking about. Okay, so the answer here is going to be apex of lung. Okay,